Let's imagine what it might be like for an inquiring mind in history, say a few hundred years ago, to suddenly become aware of discoveries in modern physics and to see the limited view from which his or her collective was engaging with what it meant to be human. Let's apply this exercise in imagination to the way that our collective engages with what it means to be human today. How might this impact our access to waking up in wonder every morning? The way that we conduct ourselves and interact with our loved ones, our children, our global siblings across the planet. How might this alter the activities that we choose to place our attention on, and the way that we engage with the elements of ourselves, our ego, our humility? Without further ado, I'll move toward today's readings. Today I'm reading from Stephen Hawking's A Brief History of Time. Enjoy. Page 49. All our theories of science are formulated on the assumption that space-time is smooth and nearly flat. So they break down at the Big Bang singularity, where the curvature of space-time is infinite. This means that even if there were events before the Big Bang, one could not use them to determine what would happen afterward, because predictability would break down at the Big Bang. Page 51. In Friedman's models, the galaxies are all moving directly away from each other, so it's not surprising that at some time in the past, they were all at the same place. In the real universe, however, the galaxies are not just moving directly away from each other, they also have small sideways velocities. So, in reality, they need never have been all at exactly the same place, only very close together. Perhaps then, the current expanding universe resulted not from a Big Bang singularity, but from an earlier contracting phase. As the universe had collapsed, the particles in it might not have all collided, but had flown past and then away from each other, producing the present expansion of the universe. This is referencing the work of Roger Penrose in 1965. Using the way light cones behave in general relativity, together with the fact that gravity is always attractive, he showed that a star collapsing under its own gravity is trapped in a region whose surface eventually shrinks to zero size. And, since the surface of the region shrinks to zero, so too must its volume. All the matter in the star will be compressed into a region of zero volume, so the density of matter and the curvature of space-time become infinite. In other words, one has a singularity contained within a region of space-time known as a black hole. For technical reasons, Penrose's theorem required that the universe be infinite in space, so I could in fact use it to prove that there should be a singularity only if the universe was expanding fast enough to avoid collapsing again. Page 57. The uncertainty principle had profound implications for the way in which we view the world. Even after more than 70 years, they've not been fully appreciated by many philosophers and are still the subject of much controversy. I'm skipping down a bit here. One certainly cannot predict future events exactly if one cannot even measure the present state of the universe precisely. In general, quantum mechanics does not predict a single definite result for an observation. Instead, it predicts a number of different possible outcomes and tells us how likely each of these is. For some purposes, it is helpful to think of particles as waves, and for other purposes, it is better to think of waves as particles. An important consequence of this is that one can observe what is called interference between two sets of waves or particles. That is to say, the crests of one set of waves may coincide with the troughs of the other set. The two sets of waves then cancel each other out, rather than adding up to a stronger wave as one might expect. The following is in reference to the so-called Two-Slit experiment. A light source sends a particular wavelength or color toward these two panels or partitions, the first of which has two slits in it. Much of the light stops at this partition. Some goes through these slits. And the following is what we can observe. If electrons are sent through the slits one at a time, one would expect each to pass through one slit or the other, and so behave just as if the slit it passed through were the only one there, giving a uniform distribution on the screen. In reality, however, even when the electrons are sent one at a time, the fringes still appear. Each electron, therefore, must be passing through both slits at the same time. Since the structure of molecules and their reactions with each other underlie all of chemistry and biology, quantum mechanics allows us in principle to predict nearly everything we see around us within the limits set by the uncertainty principle. In practice, however, the calculations required for systems containing more than a few electrons are so complicated that we cannot do them. Page 70. Dirac's theory was the first of its kind that was consistent with both quantum mechanics and the special theory of relativity. It explained mathematically why the electron had spin 1/2. That is, why it didn't look the same if you turned it through only one complete revolution, but did if you turned it through 2 revolutions. We know now that every particle has an antiparticle with which it can annihilate. There are 2 kinds of electric charge, positive and negative. The force between 2 positive charges is repulsive, as is the force between 2 negative charges, but the force is attractive between a positive and a negative charge. A large body, such as the Earth or the Sun, contains nearly equal numbers of positive and negative charges. Thus, the attractive and repulsive forces between the individual particles nearly cancel each other out, and there's very little net electromagnetic force. However, on the small scale of atoms and molecules, electromagnetic forces dominate. The electromagnetic attraction between negatively charged electrons and positively charged protons in the nucleus causes the electrons to orbit the nucleus of the atom, just as gravitational attraction causes the Earth to orbit the Sun. Page 88. In order to understand what you would see if you were watching a star collapse to form a black hole, one has to remember that in the theory of relativity there's no absolute time. Each observer has his own measure of time. The time for someone on a star will be different from that for someone at a distance because of the gravitational field of the star. Suppose an intrepid astronaut on the surface of the collapsing star, collapsing inward with it, sent a signal every second, according to his watch, to his spaceship orbiting about the star. At some time on his watch, say 11 o'clock, the star would shrink below the critical radius at which the gravitational field becomes so strong nothing can escape, and his signals would no longer reach the spaceship.